So I've got my announcements up here. Homework 4 is due today on Blackboard. I think most people have finished that up. And I posted the next 2 assignments up there as well. The material we're about to get into, I'm really excited about because we have been building up to Fourier series. I've been mentioning them a lot. But unfortunately, we need to do a little bit of like calc stuff. And so homework 5 is only, I think it's like 4 questions, and I don't think it'll be terrible, although one or two might be a little tricky, in preparation for homework 6, which is doing Fourier series stuff. I've got project 1. I know most people submitted that, and I saw those. I'll get grading those over the weekend probably. And I've been working on getting project 2 ready to go to pass that out. I've also graded test 1. I forgot to mention that last time. I had it graded last time. I just forgot to say I had, and that is up on Blackboard. I'll post solutions to that up there in the near future. I hope everyone was able to print out Chapter 5 notes. Does anyone have any questions about anything before we get started with Chapter 5 notes? Anything you want to talk about homework-wise, questions about general things? I don't know, anything on your mind?
Are you going to be available after this class to talk about homework?
Yes, I actually already have a scheduled meeting with Bradley, so anyone who wants to stick around after class and talk about homework, we can do that. You're talking about homework 4?
Yeah, homework 4.
Yes, we can do that.
All right, cool.
Other thoughts? I feel like I was just going to say something else, and now I cannot remember. Anyway, I'm going to get started. So, as I mentioned, Chapter 5.2 is Fourier series, is where we start to talk about Fourier series, at least. It's a really cool topic that involves a lot of the things we talked about, like projections, inner products, all that kind of stuff. But in order to do those things, maybe let me just put a future page up here real quick. Just to give you an idea of what the next, I think, 10 to 15 pages are about. It's like a bunch of calc stuff that you've probably seen before, maybe taking it a little bit further, because here's just an example of something we'll see later. This is from later in Chapter 5. We want to be able to do like kind of complicated integrals that require integration by parts, for example, and it's helpful to know certain tricks that'll help us with these integrals. So that's one of the things we're going to review is like, how do you do integration by parts in a really quick way? That's something called tabular integration. And the other part of that is Fourier series are a bunch of piecewise continuous functions. And so if we want to talk about piecewise continuous functions, we should know what like piecewise and continuous mean. And those are topics that are often challenging in calculus. And so before we really dig into Chapter 5, I like to start with review of some calc topics. And based on some of the past calculus knowledge some of you have been displaying, I think this is probably a good idea to sort of review some of these things. So it gets a little mundane, but I hope it looks familiar, and I hope these are the type of things that now that you're a little more mathematically mature, if you didn't really like, continuity and limits and things like that, when you first looked at it, I hope it's a little bit better this time around. Okay, so the first thing we want to start talking about is what a periodic function is. This is something I talk about in pre-calc, but we're going to talk about it in a little more complicated sense. And we want to talk about periodic functions because Fourier series are periodic functions, or they approximate periodic functions. So what does it mean to be periodic? Well, this is what it means mathematically. It means that the function at some time t is the same as the function at some p steps later. And so in other words, if you shift the graph by p units, it lines up with what it did p units before. And so the really common, and we say that the value of p is called the period. And so the common one that we've all seen before is are the trig functions. So like sine and cosine, for example. So I'm going to do a quick graph of sine. Again, pre-calc topic, we know sine does this kind of thing. It bounces between -1 and 1, and it goes both directions, of course. And this is periodic. I mean, you can just look at the graph and see that it's periodic, right? So this is just like visually showing that it's a periodic function because the graph just goes up and down and hits the same point over and over again. So visually showing how sine is periodic. And what is the period of sine? This is a question I'm posing to anyone who remembers anything about trig. Does anyone remember anything about trig? How far does it take you to repeat sine or cosine? Or maybe another way to phrase that is, how long does it take one to walk all the way around a unit circle? You start here at 0, and then this would be one period. So this is one period, let me do a different color, would be from right here to right here. This is one period because that picture, the thing I outlined, you just copy and paste it, and there it is again, right? Or you can copy and paste it this way, and there it is again. And so that's one period. What's the ending point of that period? Like, what's this value right here? Anyone? Oh, sorry, I didn't see anyone typed stuff in. 2 pi, look at the chat. Got it. And for some reason, I didn't get like a chat notification. Okay, anyway, yeah, so it ends at 2 pi. So this is just visually showing how sine is periodic with period 2 pi. And so the idea is like this point, right, just gets repeated right over here. And if this point right here is pi over 2, then this point right here should be 2 pi later than that. And pi over 2 plus 2 pi is 5 pi over 2. And that happens to be that point right there. So it's just saying, like, when you go 2 pi later, you're going to get the same output value. And again, that's what Fourier series we'll see are just periodic functions that repeat. And so we want to have an idea what that means. Now, maybe we can show this. This is just visually showing it, but maybe we can throw a little mathematics on this and show it a little more carefully. So let's show that sine of t is period with 2 pi, and then talk about what is the period of some transformation of cosine. So in the first problem, if we want to show sine has period 2 pi, we want to show that this property is satisfied with p being 2 pi, excuse me. And so we want to show that sine at the current time step is the same as sine 2 pi time steps later. Right? That's just like applying this definition with this. This is our p value. Does this look familiar to anyone? What could we possibly do with two things being added inside sine? Think back to your trig or maybe calculus. What do you do? What's a tool in your tool belt that you can use when you have two things being added in there? Thoughts? Remember that? There's some relationship or formula that we can use there.
Wasn't it like substitution?
So if you wanted to integrate this or do something like that, yeah, you would probably use substitution because you usually want to remove the thing that's inside sine. But if we wanted to evaluate this, we could use what's called the addition or subtraction formula. Again, that's something I also teach in pre-calc. Just going to join this chat from my other computer here so I can see what's being projected. Okay, so the addition subtraction formula, I don't know if you remember this. Let me write it down in case you don't remember it. It says that when you add two things inside of sine, you can break it up like this: sine of s, cosine of t, plus cosine of s, sine of t. And so we can apply this sort of relationship, this formula, to t plus 2 pi. And then, so that means that sine of t plus 2 pi, if we use that formula, would be sine of t, cosine of 2 pi, plus cosine t, sine of 2 pi. And I'll also remind you, if you don't remember this from trig, cosine's the x value on the unit circle, and y is the sine is the y value. And so the cosine value, the x value at 2 pi is 1. That just equals 1. And then the y value at 2 pi is 0. And so this whole term just goes away because that ends up being 0. And then you multiply 1 times sine. So we just showed that sine of t plus 2 pi is equal to sine of t. Well, let me actually finish writing it first. I guess I didn't finish writing that simplified version. So this equals just sine of t. In other words, I'm off the screen here. Let me move it up. Since we just showed that sine of t equals sine t plus 2 pi, we've further shown that sine of t has period 2 pi. Okay, so just again reminding about some pre-calc stuff, some calc topics. What is a period? How can we actually show something has a certain period? We want to be able to show that t plus p equals sine of t. Oops, excuse me. Thoughts about that part? Let me just ask you again. Was everyone able to print these notes out? Because I have hard copies of them that I can like snail mail you if that would be helpful. I don't know if that would be helpful, but anyone need that?
I was able to print them.
Matt would like them. Okay. Matt, are you living near campus still? Okay, maybe I can just drive those down to you. I may have actually recycled them. If I can find them, I may just drive those down to you and like drop it in your mailbox or something. I've been quarantined for like 2+ weeks, so I'm legit, but you scare me. Let me make myself a note. Okay, what about the second part of this question? So the second part is, we can assume, since sine and cosine are just translations of each other, let's go ahead and assume that normal sine, cosine I mean, has period 2 pi. And we could do the exact same thing to show that using the addition subtraction formula for cosine. So assuming that cosine normally has period 2 pi, what does this do? Do you guys remember this type of transformation? Again, this is like a pre-calc thing. This is multiplying the input values by k. Didn't remember what that does to a function. So if cosine usually has 2 pi, then what does f of t equals cosine of kt do to cosine? That's a what? What kind of transformation is that? Well, if you don't remember, it's a horizontal shrink. Oops, horizontal. We're multiplying the input values by k, and so that does things side to side to the function. It does horizontal things. And so this is a horizontal shrink of cosine by a factor of k. And so if cosine usually has a period of 2 pi, and then we shrink it in by a factor of k, what do we think cosine of kt has a period of? I'm going to write that down. If someone's got an answer, please chime in. So if cosine of t usually has a period of 2 pi, what do we think happens to cosine of kt, which has been shifted in by a factor of k? Right. So what I mean by horizontally shrunk is if it's usually this wide, it gets shrunk in by a factor of k, like it goes down. So what do we think cosine of kt would have a period of what?
Would it just be 2 pi divided by k?
Yeah, so not k, but you divide 2 pi by k. Good. So it would have a period. It's normally 2 pi, but then you're shrinking it in by k, and so we would just divide 2 pi by k. And this is, I literally teach this in pre-calc. I did this like last week, or this week online. is if you've got a horizontal shrink, you adjust the period by dividing 2 pi by k. Okay, so just some reminders, a little couple things. We're going to be using sine and cosine quite a bit with respect to Fourier series. We project them using the basis sines and cosines. And so I just wanted to remind you about what those are. So we use sine and cosine because Fourier series are periodic, and so are sine and cosine. So we sort of take this existing periodic function and then we force it to match other periodic functions. Kind of similar to homework 4 number 1, where you're projecting the exponential onto the actual function, except you do it with periodic functions that are more complicated than that one. All right, I'm going to flip this page. The next page is just some references more than anything, but there's a couple reasons I wanted to show this. So first reason is this is a very sort of common and interesting or powerful relationship. So e to the I theta equals cosine theta plus I sine theta. And then, so this is a relationship that exists, and then you get from here to here, what would I need to plug in for theta to make this expression become this one? What do you think about that? So there's no i's in this, so we would want the sine to be 0. And then we would want cosine to be -1, so that when you add it to the other side, you get this.
Yeah.
Pi. Yeah, so if we plug in theta equals pi, nice, then we would get down to this expression. And this is sometimes regarded as, quote unquote, the most interesting equation in mathematics, is what some people would say. But the sort of far-reaching applications that we can often see with that relationship there is not necessarily for this course, but it is a nice thing to know because it helps us solve certain integrals. Like, remember back when we were looking at integrals of sine and cosine, we rewrote them as e to the raised to some power, so that's nice sometimes. And it's going to help us do this this integral down here. And there's actually one of these very similar to this in the homework that looks a lot like this. So keep this relationship in mind up here, and it's going to apply down at the bottom of this picture. So this is a lemma. So this is sort of like a theorem type thing, and it's telling us when we integrate e to the ikx with respect to x from x0 to x0 plus 2 pi, so we're like going 2 pi down the line, it's equals 2 pi if the k here is 0, and it equals 0 if k is anything but 0. And so there's a problem like this in the homework, if I'm not mistaken. Let me just, I just want to make sure it's in this homework and not the next one. I'm almost positive. Let me just verify. Yeah, so there's a similar one that's going to involve a kind of, that's going to be very similar to this. We're showing the inner product of cosine, and cosine is 2 different things. It's going to look kind of similar to this. Number 4 in the homework is kind of similar. But anyway, it's basically 2 cases, right? So there's 2 cases here. Either k is 0 or k is not 0. And so if you want to prove this, you need to either assume k is 0 or assume it's not 0. And so that's the way you should approach the homework problem. Let's just walk through this real quick. If k is 0 in this expression, then this is just e to the 0. And so you're just integrating 1. And when you integrate 1 over the integral, you're going to get x0 minus x0 plus 2 pi, or the other way around. And so you're just going to cancel out the x0s, and your answer is going to be 2 pi. So that's why you get that when k is 0. And when k is not 0, so if you want to keep k sticking around, then you integrate this thing, which is a pretty straightforward integration of e. You would plug in the bounds, which would end up looking like this. That's what you get when you plug the bounds in. And then if you factor out e to the I k x0, you're left with this value. And then it turns out you can also rearrange, so this value can be rewritten like this. Right? You can like factor out the 2k in some sense. And then the equation up here tells us, well, e to the I theta actually equals -1. And so this e to the I theta right here, I pi, excuse me, equals -1. And so you have -1, excuse me, you'll have -1 raised to an even, so it's 1. And so you get 1 minus 1. And so that's how things cancel out to be 0. But again, it comes from this fact, which is from above there. I was just about to say something else. Oh, why do we need to break this down into two cases? Why can't we just assume K? Why do we have to assume K is 0 in a separate case? And why can't, or in other words, why can't K be 0 in this case? Or if you have another question about that, you have to answer it. But I wanted to at least pose that to you. What did you think about that? Why do we need to break it down into K being 0 and K not 0? What about this makes it so K can't be 0?
Oh, the denominator?
Yeah, so right when you do this integration, you end up dividing by K. And so K can't be 0 from here on out, or else you'll divide by 0. And so that's why you need to break it up into two separate cases, which is a very common thing in math. Like you sort of say, oh, oops, when that happens, I need to think about it being 0 or not. And you kind of do two separate things separately. Okay. Again, just kind of reminding us about some integration things. We'll see integrals that have e's in it and things like that moving forward. So just kind of reminding you how some of that stuff works. And we are going to look at some one-sided limits and things like that on the next page. Can I clarify anything about this page? All right, I'm going to flip it over and take a look at that. So the next page is a whole bunch of definitions, and I'd like to just look through them and remind you what they mean, remind you what they're saying, and see if you have any questions about them. So there's 4 definitions on this page. Let me go ahead and number them. There's it's kind of like, well, I guess there's more than 4 definitions, but there's 4 main concepts here. There's number 1, one-sided limits, excuse me. There's number 2, one-sided derivatives. Number 3 is the definition of continuity at a point. And then number 4 is the definition of piecewise continuity. I know there's just a list of things, 4 different concepts. One-sided limits, one-sided derivatives, continuity, and then piecewise continuous. So let's read these things one at a time here. So first, we say that a function has a left-hand limit at a specific point x0 if the function value at that 0 approaching from the left, so this negative sign that's up in the superscript here that almost looks like an exponent, means you're approaching that thing from the left. And so it's telling us the limit as x approaches x0 from the left of the function equals what you get when you plug x0 from the left into the function. And then the exact same definition is on the right, except the plus sign is there. And so you're approaching x from the right. And so this is the kind of thing, I haven't taught calculus in a few years, but I just remember when I did teach calculus, this is the kind of notation and concept that sometimes people got really confused with. Now, usually it's maybe not math major, so I don't know, maybe you guys are okay with this stuff, but I do want to just reiterate this in case you haven't seen this in a while, because of a lot of it is just notation. People get very confused by the notation lim x arrow x0 with the minus sign. Or the same thing, but with a plus sign. And so as a reminder, the way you read that, you would say the limit as x approaches x0 from the left or negative direction, that would be x0 with the negative, or right, which would be the positive direction. And so that would be the x0 with the plus. And so we'll look at some, if you turn the page, we're going to look at a piecewise example here where things are broken up. And what you do is they switch over at 0 and 1 here. And so the left-hand limit is going to be different than the right-hand limit when we look at this specific example. Anyway, we'll see that on the next page. We'll look at it. Can I clarify something about the notation about these first two things? Does anyone remember this from calculus or desperately not remember it? Just might be helpful to know either of those things here. Also, let me know what's going on with the screen, if it's blurry or whatever. For some reason on my screen, it looks like my top of my page is like way up here, but when I look at my other screen, it's like way down here. Is this the top of your screen?
Yeah.
My pen on everyone's screen?
Yeah, that's the top.
So if I go like this, the tip is off?
Correct.
Very strange. Okay, mine has a different setting or whatever. Anyway, thoughts about one-sided limits, I mean. We'll look at an example on the next page, but folks remember that? Okay, so that's definitely something you've seen before, so I do hope you remember it. What about the bottom of the page? Let me actually ask that. Is this on the page?
No. Yeah, right there.
Okay, that's good to know. All right, so what was I saying? Oh, I was saying people have definitely seen one-sided limits before. So this first stuff, whether you remember it or not, I know you've seen it. I'm not sure if you've seen one-sided derivatives. I know I hadn't really, it wasn't familiar to me until I took this class the first time. So notice this is the definition of a derivative. So without the minus sign or the plus sign, that's the definition of a derivative. You take the limit as h goes to 0 of f of x plus h minus f of x over h. You remember that, like, hating that in calculus, anyone?
Yeah.
It's the same thing here, except you don't hate it, and it's got the negative sign and the plus sign on it. And so it's the exact same definition as it was in calculus, except instead of just approaching 0 in general, we're approaching 0 from one particular direction. And so these definitions are the same as normal from calc, except h is approaching 0 from the left or from the right. I believe we see some of those examples. You may not see one of those. We do see one of those. Yeah, we'll look at an example in a couple pages of that. The other thing I'd like to just mention to you are these piecewise continuous and continuous and piecewise. So this is the definition that you saw in calculus, which says a function is continuous at a specific point if the limit as x approaches that point of the function equals what you get when you plug x0 into the function. And so for the thing that you needed to remember, so for in order for this to be true in calculus, that means that f of x0 needs to be defined, and both left and right side limits have to exist and equal each other. And so like this simple statement involved kind of like 3 or 4 different things, right? And so this requires 1, the function to exist at that point. 2, the left-hand limit at that point equals the right-hand limit. Oops, x approaches x0 from the left. And the third thing it requires all those things to be equal. So it requires number 1 to equal number 2. And so we will see some examples of that. But if you remember from calculus, that's sort of the process of proving a function is, or showing it's not continuous at a point. It's going through those 3 things and seeing whether or not they're all true. And then the last thing, so this is the definition of being continuous at a point. Piecewise continuous is very similar, except we're on an interval AB, and we would say it's continuous at every single point on the interval, except for a finite number of points. And moreover, at those specific points, the left and right-hand limits have to actually exist. And so maybe I'll just make the note, like, we're going to look at one of these on the next page. See next page, for example. So I'm going to come back to these definitions as we go here, just some reminders, and so you have them all kind of on one page. Can I clarify anything about those? Any patient things or anything about that? Is my audio coming through okay? I think that should be fine.
Yeah, you sound good.
Great. Okay, so let's do an example here using some of these definitions. So I'm going to flip the page here and take a look at that. So here is a piecewise function. Right, we know it's piecewise because it's broken into pieces. I hope that wasn't redundant, but right, it's three different polynomials on the interval -2 to 2, and they are broken up into pieces. And so we're going to show that this function is piecewise continuous on that interval. So what that means, based on the last definition, is it's going to be continuous at every single point except for a finite number of points. Oops, on the bottom. Except for a finite number of points, and at those finite number of points, the left and the right hand limits exist. So that's what we're thinking about here. It might be helpful to draw a picture of this one just so we know what we're looking at here. I remember being very intimidated by piecewise functions. There's something very complicated looking about that, especially when you're kind of early in your math career. But it's really not that bad, right? It just tells you how it's broken up, what intervals it's broken up on, and what the values are on that interval. So, for example, this is telling us from -2 to 0, the function looks like -x. So that would look like this then. Starts at 2, so -2 here, we're going to 0. And we've got an open circle here, closed circle here, so it'll be something like this. So that would be the first piece, right? That's the function -x from -2 to 0. And then it's telling us between 0 and 1, the function's just up at 1. And it's got a closed circle, open circle situation. So we're here at 1, got a closed circle starting, and then it's going to go to +1 with an open circle. And then the last piece tells us it looks like x squared minus 1 between 1 and 2. And at 1, this is 0. And at 2, this is up at 3. And so we're going to go up to 3 here. Closed circle. It's got the x squared shape. And so it's going to do this kind of thing up to there with another closed circle right here. And so just kind of, it's helpful if you remember this from calc. It's helpful to know what the picture looks like when you're thinking about these one-sided limits. Because you can just look at the picture and pick off the limits that way. Thoughts about the shape of that at all? Does that seem okay? I didn't mess that up at all, did I? I think that looks all right. Just gonna let people finish writing that down and see if there's a question. Guys have any horror stories about moving classes online yet? I'd love to hear something.
Yeah, one of my classes has like 22 people in it, and we all joined the call, and the professor couldn't hear any of us, but we could hear him and hear all of each other. So for like 20 minutes, we were trying to tell him to turn his mic up or turn his volume up and stuff like that, and he never figured it out. So we all just had to type answers into the chat. And for some reason, he had 2 cameras going, and one of them was on the floor, like facing up at him, and the other one was like his regular one. We don't know why, but he wanted.
Is this an older professor potentially?
Yeah, he's a little bit older. He's my World Civ professor.
Yeah, I mean, I feel for these people who are kind of technologically not illiterate. Some of them are technologically illiterate, but at least like some of them have tech phobia even, and now they're like forced to do it. And I can't imagine what it's like. It's hard for them too. I imagine it's very challenging for students too. These people have been doing the same thing for 30, 40 years sometimes, and all of a sudden they have to switch and on the fly in a week, and I can only imagine. Anyway, anyone else have some good stories there? Is anyone's class not able to move online? Is anyone doing like an art class or something like that that's It's going to have an issue with that. Okay, well, we can keep going with this one then. Are there questions about the graph? Everyone's okay with that? So if we want to show this thing piecewise continuous, we want to show that it's continuous on every single point except a finite number, and that the one-sided limits exist. And so the thing to note here is we'll use a little bit of a shortcut, which is that each one of these things are polynomials separately. And so since each one's a polynomial separately, they're going to be continuous on their domain. And so what we really need to check here is just the one-sided limit. I want to just write that down. So each piece is a polynomial. And because of that, they're therefore continuous on their domains. That's a theorem that absolutely comes out in calculus. Polynomials are continuous. So that means we just need to check the one-sided limits at the discontinuities at the intersection points. And the intersection points are, it starts at -2. The first intersection point is 0. The second intersection point is 1. And the third one is 2, or the fourth one. And so we just want to look at the one-sided limits at those various places. And so let's start doing that. So like when we write down, for example, I lost my pen. Here we go. We want to write down, say, the limit as x approaches to -2 from the right. So we want to look at this point and we want to approach it from the right. So that means we're walking along this picture from the right-hand direction, from the positive direction, and we're trying to approach -2. So that means walking along this piece like I'm doing with my pen over and over and seeing what we're approaching. Well, as we approach -2 along this piece, the y value is approaching 2. And I know it's approaching 2 because this piece uses the function -x. And when I plug a -2 into -x, we get 2, right? So in other words, if I want to do the right-hand limit at -2, that means doing the right-hand limit of the function -x, because that's what the function equals on that piece. And so it's a polynomial, so I can just plug -2 right in, and you get +2. So we're just checking the one-sided limits. We want to see that they all exist, right? That's the definition of piecewise continuous. And so we check the first one. Now, this -2 only had one piece that was connecting it. But when we check 0, there's 2 pieces, right? There's a piece coming down from this side at -x, and there's a piece coming over this side at the function 1. And so when we check the limit as x approaches 0 from the right and left, I guess I should do left first since we're moving left to right. We have 2 different functions to look at. And so if I wanted to do these 2 pieces, when I'm moving from the left here, I'm going to be walking along on this piece. And when I'm approaching it from the right, I'm going to be walking along on that piece. And so this piece is going to be -x, and this piece is going to be the function 1. And again, they're both polynomials, so we can just plug the numbers right in. And so this ends up being 0. This ends up just being 1. And so the right and left-hand side limits exist. I think it's important to note that the right and left-hand side limits exist. We get a number there. But they're not equal to each other. And so that means it's not continuous at the point, right? Going back to the definition on the last page here, if we wanted to be continuous at x equals 0, we would need f of 0 to exist, which it does. And we'd also need the right-hand, left-hand limits to equal each other. Oh, I actually meant, I wrote this down wrong. Number 2 here should say these 2 things both exist. everyone see that? Sorry, I wrote the same thing twice for 2 and 3. What I had wanted right here was the function exists at the point, the left and right hand side limits both exist, and the third thing is that they equal each other. So sorry about that. So no, in other words, number 1 and number 2 are satisfied in this, but number 3 is not satisfied in our particular example. And so while these two functions have left and right hand limits, they're not equal. They're different. And so this function is not continuous at x equals 0. That's the kind of thing that we looked at in calculus, right? That's how I put questions on tests like this that say like, oh, show this function's not continuous at x equals 0, and this is how you would do that. At this point, you should either remember some of the stuff or it's all feeling brand new. Does anyone want to clarify something for someone who this is feeling very new to? Maybe where something came from or why I use a certain function or anything like that? Okay, let's finish it off then and look at the other one-hand side limits. So let's look at the limit as we approach. We'll look at 1 and 2. So the limit as we approach 1 also has two-sided limits. So we have 1 from the left, and we have approaching 1 from the right. And when we're approaching it from the left, we're still on the function 1. And when we approach it from the right, we approach 1 from the right, we're on the function x squared minus 1. Again, both polynomials, so we can plug the numbers right in. That's going to be 1 minus 1, which is 0. And so the one-sided limits exist again, right? We got numbers out, but they're different, so it's not continuous. Just going to write same response there. And then the last piece is just at 2. We could do the one-sided limit as we approach 2 from the left. We can't approach it from the right because the function doesn't exist on the right-hand side there. And so this is going to be x squared minus 2 again, and so we get 3. Okay, so is this function continuous or piecewise continuous?
No.
What was that, Danny? I think it was Danny. Danny said that.
Yes.
Yeah. So in order to be piecewise continuous, it needs to be continuous on the interval except at a finite number of points, and the one-sided limits need to exist. And so it's continuous on everything except for at 0 and 1, so a finite number of points. And all the one-side limits exist. And so the answer is it is piecewise continuous. So cis f of x is continuous at all points on the interval. So all points on -2 to 2, except 0 and 1, which is a finite number. And all the one-side limit exists. This is piecewise continuous. F of x is piecewise continuous. I think that was worth looking at. We will see a couple more kind of similar examples. There's 2 more actually that we're going to look at that are going to look at different aspects of this. But I'm hoping, or at least in my experience, I kind of felt like it was worth looking at this thing one more time because I remember how confusing it can be for students, especially you might not have seen it in like 3 years or something or more. So thoughts about that at all?
Yeah. So on the page with the definitions, so number 3 is talking about just like specific points, and then 4 is talking about the whole interval.
Yes, correct. So this one's talking about at a specific x equals x0, and this one's talking about on an entire interval, right?
Okay, so that's like, so we used 3 at the points -2, 0, 1, 2, and then we looked at what happened there to see number 4.
Right. Yeah. And we use the kind of the cop out a little bit by saying, oh, well, these are polynomials, and so we're not going to worry about any of the middle points because we know they're continuous there, which is usually the case in general anyway. But the thing is with these Fourier series, they're going to be piecewise continuous functions that may or may not line up with each other at the intersection points. And so we just want to have an understanding of sort of like what that means mathematically. It means that the individual pieces might be continuous, but just maybe not at their connecting points.
Okay.
Other thoughts? Okay, I'd like to do a couple more examples of applying those definitions. So that's what's on the next couple of pages here. The next one is, so we just did like a piecewise continuous thing. This one is looking at one that is not piecewise. Oops, I just gave away the answer. The question is f of x equal 1 over x continuous on minus 1 to 1? Is it piecewise continuous on minus 1? So let's remind ourselves what 1 over x looks like. 1 over x is a function that does this. So there's an asymptote, there's a vertical asymptote at 0. And then the function like explodes up to positive infinity that way, and then it goes down to 0 right there. And then this one explodes down to negative infinity, and then it's one approaches 0 on the left. And so we're thinking about the interval minus 1 to 1, which maybe is like something like here, minus 1 to 1. So this is what 1 over x looks like. Okay. So thoughts about it being continuous on minus 1 to 1? Let me ask Nick specifically, since people are being quiet. I want to see if they're there. Nick, is this thing continuous on minus 1 to 1?
No, because of the asymptote.
Good, yeah. So like, one way to think about it is if we were trying to trace our finger along the function here and we wanted to jump over, we'd have to take it off and go over to this piece, right? That's how I teach it sometimes. If you trace your finger and you have to lift it up, it's not continuous. How would we sort of say that mathematically, though, using the definition? So the definition says if we're going to be continuous at 0, so x0 is 0, we need these three things to be true. Which one of those things are violated? Let me stick with Nick.
Oh, sorry.
So 2 is violated. Any others?
Would 1 be violated too?
Say that again. Which one?
1.
Yeah, 1 is also violated. And so if 1 and 2 are violated, they can't be equal. That means they're all violated in this case, right? Because f of 0 doesn't exist because there's an asymptote. The one-sided limits don't exist because they approach infinity. And since both of those things don't exist, they can't possibly be equal to each other. Right, like, so if we did the left-hand limit here and we're not approaching anything, this thing just goes down to negative infinity. So 1 over x is not continuous at x equals 0 because the limit as x approaches 0 from the right doesn't exist, and it doesn't exist from the left, which means the overall limit doesn't exist. And for that matter, it's not defined at 0. So pretty much everything fails at 0. But that's a finite number of points, right? So it's not continuous at 0. So that's just a finite number of points. And so it could still be piecewise continuous. But is it piecewise continuous? If it was going to be piecewise continuous, we would need the left and right-hand side limits to exist. Thoughts? Let me throw it over to Matt. Is this thing piecewise continuous? So x equals 0 is a finite number of points. Matt, you with us? It's not here? Yeah, he's in here. Is this thing piecewise continuous? So it's not continuous at 0. because of all these reasons. But 0 is just a finite number of points. And so piecewise continuous says it could not be continuous at a finite number of points as long as the left and right-hand side limits exist. Thoughts about that? So the question is, do these right and left-hand side limits exist at 0? Right, no, because they go to infinity, exactly. So we already said that they don't exist right here, exactly. So even though x equals 0 is a finite number of points, we know that the limit as x goes to 0 from the left is negative infinity. And if we approach it from the right, it's positive infinity. And in both those cases, they both don't exist. And so it's not even piecewise continuous since one-sided limits don't exist. This is trying to drive the idea home that like just because something has a finite number of discontinuities does not mean it's necessarily piecewise continuous. That's what we're trying to do. So let me just add one more note. So since one-sided limits don't exist at x equals 0, 1 over x is not piecewise continuous on -1 to 1. Piecewise. All right, what do you think about that? Does that seem okay? Can I clarify something there? Okay. The last thing I'd like to do is just look at one-sided derivatives to see if that makes sense. I know that can be confusing too. And so that's the last thing I'd like to do. I'd like to make sure we get through the calculus sort of review today, or the limit review, I should say, because next time we can look at reminding you about how to integrate even and odd functions and giving you some shortcuts to do some integrals. That's what I think the next class will probably focus on. Yeah. Okay, cool. So this is the last one we'll look at. It's another piecewise function. So let's consider the below function. You can see it's being plotted here. And this one's telling us that, or it's asking us, let's find the one-sided limits at all the intersection points. And let's find the one-sided derivatives at the two middle intersection points. So the 0, 1 where this thing flips over, and then the 1/2 one where that flips over. And so the one-sided limits is the same thing from the first page. And so I wanted to see if you would just do those yourself and see if that makes sense. I'll start writing them down here, but what this is asking us to do for the one-sided limits is to approach -1, 0, 1/2, and 1 from one side. So we're going to look at this, in other words. -1 from the right, 0 from the left, that should be an x. Just going to write down all the things I'd like you to think about for a second. That equals something, that equals something. X approaches 0 from the right equals something. X approaches 1/2 from the left. 1/2 from the right. And then 1 from the left. So just take a second and see if you can if this makes sense, right? So in the first one, you're walking along this line towards this point. And the second one, you're walking along this line towards this point. The third one, you're walking along this line towards this point, etc. Is that process, if that's not clear, I'm happy to reiterate it, but if this makes sense, I'm not going to belabor the point. Can I clarify how we do one-sided limits? You okay about that? So then you should have gotten this, right? When you're walking along this line, you're up here at 1. When you're walking along this line, you're still up here at 1. When you're walking along this line this way, you're getting down to 0. When you're walking along this line and you're heading up here, you're halfway between 0 and 1. So that's 1/2. And you can know it's that point because you're along the line x, right? So you can just plug this right into x. When you're walking along this line and you're approaching 1/2, you can plug 1/2 in here, and you would get 1 minus, oops, not 1 over, minus 1 minus 1/2 squared, which is going to be 3/4. It's going to be 1 minus 1/4. And then the last one, when you're walking on this line towards here, you're getting down towards 0. Looks like this one's a little bit past 0 for some reason. Sorry about that. I did want to just take a little more time to think about the one-sided derivatives because I think those are the ones that are maybe a little more confusing. And so, are there questions about that, about the one-sided thing before, about these ones at all? Okay. So let's look at the one-sided derivatives then. So we're going to go at 0 and 1/2, right? And so back to the definition here. If we're going to do the one-sided derivative at a specific point, so x0 is 1/2 in this case, then we need to do the left side derivative at 1/2. I'm sorry, we need to do the left side derivative. No, I'm confused here. Yeah, I'm sorry. We're going to use these definitions. I thought there might have been a typo in there. So we're going to let h go to 0, and so the h part's going to go to 0, and then the function value that we end up using depends on what piece of the graph we're on, right? And so if we're on the right-hand side of a point, for example, or the left-hand side, we're going to use one piece, and if we're on the right-hand side, we're going to use a different piece. And so maybe let me write down the first one and see if it makes sense, and maybe you think about the second one for a minute. So let's do the one-sided derivative at 0 first. So we want to do f prime of 0 from the left, and we also want to do f prime of 0 from the right. Those are the two things we're looking at from that definition. And so we're going to do the limit as h goes to 0 from the left, and we're going to do limit as h goes to 0 from the right. Of the same thing, f of x plus h minus f of x over h, and the same thing here. So I'm just writing down the definition so far. The thing that ends up making them different is when you're approaching it from the right, the f of x is a different thing that you're using than when you're approaching it from the left, right? Like if we're talking about approaching 0, if we're approaching it from the left, we're up here in this function 1, and if we're approaching it from the right, we're over here on the function x. And so that's where things are going to come in differently. And as a quick reminder, this notation just means like, so f of x is just a function, but f of x plus h means you plug x plus h into the variable, right? So like on this one, you're just messing around with the function 1. And so you use nothing to plug into, in other words. So when you try to plug x plus h into 1, see if I slide this on. Yeah. So this is just the number 1, right? So there's nothing to plug into with the number 1. And so this first one is just going to be 1 minus 1 over h. Right, because f of x plus h is just 1, and f of x is also 1, because you're just dealing with the number 1. But on the second one, you're dealing with the function x, because you're to the right of the function of 0. And so now we're on the line x. And so if I plug x plus h into x, it becomes x plus h. Are there questions about those two? And then we can simplify. Let me simplify it and then see if there are questions. So 1 minus 1 is obviously 0. So we get limit h goes to 0 from the left of 0 over h, which is just the limit as h goes to 0, 0, which is just 0. So we just get 0 for the first one. And that makes sense, right? The slope on this line is 0. And we should get 1 for the second one, because we know that the slope of the line y equals x is 1. So let's make sure of that. When we do the subtraction, the x's cancel. And so we get h going 0 to the right of h over h. And so that just cancels into 1. And so we got x goes to 0, right? H goes to 0 from the right of the number 1, which is just 1. Let me pause there and see if there are thoughts about that. I did not have any of you in class in calc, so I don't really know. I don't remember anyone's ability to do this, or if this makes sense. If this is confusing, let me know. If it makes sense, that'd be good to know too.
I mean, it looks familiar. I just haven't seen it or done it in years at this point. But
Yes.
What you're doing makes sense.
Okay, I'm glad to hear that. And you know, I know it does. That's one of the reasons I want to look over this again. Like, I could just assume like, oh, you've taken calculus, you've seen this, let's jump into Fourier series. But I think there'd be a lot of like trying to catch up, trying to fill in backfill holes as they come up. Would I rather just sort of build up to this kind of over the course of a period or two? So that's sort of my goal here. Are there thoughts about that? Questions about that? The one-sided limit at 0? Then would you mind trying the other two or the other one? And so I'll get them started. But if you could get an answer, that'd be great. So we want to look at the one-sided derivative at 1/2. So we're going to do 1/2 from the left. I should have done left first. So we're going to go h approach 0. I almost wrote 1/2 from the left. Same exact thing, except the f of x is going to be a different value. And so this one's not too bad because you're using it's going to be the same thing as what we just did. But the other one is the one that's a little tricky. So when you approach 1/2 from the right and you do that derivative, you're using the function 1 minus x squared. And so that's going to take a little bit of algebra to get an answer for it. But just take a second and start doing that one. So the first one, I'll just do the first one since the first one is the same as the last one. You're using the same function, so it's the exact same thing. So you're going to get this again because you're on the same piece. Oops, I forgot my limit. So you're going to get this. So you get the same thing as before because it was on the same piece, right? You're just like, you're finding the derivative going down this way over here. Then you find the derivative, you go over here. And so it's the same piece, and so it should be the same value here. The second one is a little bit trickier because you're using the function 1 minus x squared, like I said. So there's a little bit of algebra involved in that. I'd like to give you just a couple minutes to think about that. Maybe we'll look at this at 3:12 or something like that. If there are questions, I'd be happy to answer them in the meantime. So to be clear one more time, when you're doing f of x plus h and f of x in this last piece here, you're approaching 1/2 from the right. And so in that case, we're on this final piece of the graph, which is using 1 minus x squared. And so I'm just going to write down this first step in case you're still a little bit stuck here. This is going to be the limit as h goes to 0 from the right of 1 minus x plus h squared. That's f of x plus h. And then this is f of x. So this is a little more involved because you've got to like square out the x plus h and do a little bit of algebra, but it's not that bad. It's not horrible. You can simplify that down. And if you know the derivative of 1 minus x squared, then you should already kind of know what the answer is here. So I'm going to sort of write the next step that you get after you do that. So when you multiply this all out and you distribute the negative sign, you get 1 minus x squared minus 2xh minus h squared minus 1 plus x squared. And a bunch of stuff cancels. So 1 cancels with 1, 1 and minus 1. We've got minus x squared and plus x squared. And so we're just left with limit as h goes to 0 from the right, minus 2xh minus h squared over h. And then you can factor an h out and cancel the one in the bottom. And so we really just get limit as h goes to 0 from the right of minus 2x minus h. And now you can plug in h equals 0, and you just get minus 2x. And so that's the derivative of 1 minus x squared, right? So just as a reminder, that's how you can sort of show it.
Wait, should it be
using the definition? Sorry, go ahead.
Sorry, no, should it be approaches 0 or approaches 1/2?
H is approaching 0.
Okay.
So f. So when we write f from 1/2 plus, that tells you what function to use. But h is the thing that's approaching 0 in all cases. So eventually you want to plug in h equals 0.
Oh, okay, okay.
Maybe I'll try to remember to show. I've got a good web app that tells you why h goes to 0. It kind of shows how this works visually. I wasn't really thinking about that. I should have gotten that ready for today, but maybe I'll try to get that ready for next time. Other thoughts about this particular one? I'm going to stop here, I think. So I'm going to stop here and we will look at even odd functions and things like that next time. Please remember that the homework 4 is due today at 5 p.m. And so you should submit that to Blackboard if you haven't done that already. And I'm around. Let me know if you have any questions about anything. And if you want to stick around and talk about questions for homework 4, I'm going to do that with some folks right now. All right. Thanks, guys. So what do you want to talk about homework 4? Bradley had some questions. I don't know if she's here. Can you hear me? Maybe, what did you want to talk about, Danny?
Oh, it looks like she just turned her mic on.
I kind of know Bradley's questions, and she's got a few of them. Did you have something that was quick, or did you have a couple of them yourself, Danny?
It was kind of a couple, like just as I was going through it. So, I mean, yeah, it's probably not going to be quick either. So if you want to start with her stuff, that's fine.
Okay, Bradley, go.
Okay. It was 5B, right? Yeah, 5B and 5C. I don't know how to do correctly.
So can you show me what you 5B and C? All right, let me talk about 5B. And while I'm talking about 5B, if you could maybe get your maple pulled up for 5C. So 5B, we know two things. We're being told that a cubed equals 2a to the fourth equals 2a squared, and we know that P of t equals a to the t p0. And what we want to show that 2 time steps later, it's twice what it was previously. That's what we're trying to show. And so maybe we can just start with this, right? And I kind of like Bradley to walk me through this, if that's okay, because we've been talking back and forth about this one, and I wasn't sure how much he was understanding. So like, if we want to show this, and here's something that tells us how to do P of t, using this, what is P of t plus 2?
AT times PO. Oh wait, no.
That would be P of t. So if I plugged in a t plus 2 into here.
So AT plus 2.
Right. Okay. Now this, what's a general expression for this? Like, what is the relationship here? How can we generalize that? Right. So in other words, 3 is here, is in the exponent here, and there's a 1 right here. There's a 4 here, and there's a 2 here. And so, and there's a 2 in both cases. So it's going to be like a raised to some power equals 2 times a raised to some other power. What is the power here? How is the powers related to each other?
I don't really know.
So let me give you that. We want an expression for a of t plus 2. So a of t plus 2 here, right? These ones are always 2 more than those. And so a of t plus 2, Danny, do you see what I'm saying here?
Yeah, so because a cubed, you just subtract the exponent by 2 and then multiply by 2. So that would just be equal to 2a to the t.
Right. So this is the relationship that you get from that. And so you can substitute 2a to the t into here, into a of t plus 2. And what do we know about this?
That's PT.
Equals pt.
Okay.
And so we just showed that 2 time steps later, you get twice what you had 2 time steps earlier.
Okay. That makes sense. I had a question on that too, so that works out.
All right.
And so just to be more clear about that, Bradley, what you had sent me something where you showed like, you specifically showed that a to the 4th equals 2a squared, and you specifically showed that a cubed equals 2a. But that's just showing it for a specific t, right? And so that's just showing, I think like you had said, for example, was like p4 equals 2p2. Like you had showed something like that, for example. That's just showing specifically for t equals 4 that happens. But this is better because this shows every single time you go 2 time steps later, you're going to double the population. This is a stronger statement that shows it in general. Do you have something that you can show me for the 5C?
Yeah, I have to find it though.
What was your other question? Do you have a question you want to ask in the meantime, Danny?
Yeah, it was also actually going to be for 5C was one of them too, just because I feel like I put it in to Maple and I ended up getting eyes for like the for whatever that value is that we wanted. I didn't think that was right.
I think it does have eyes. Let me double check.
Right, because like there's some.
I believe it has eyes.
Oh, it does. So like the dominant eigenvalue, whatever, ends up being I think.
Now I can't remember.
Of course, I didn't save it.
How would I show you my maple?
So you hover over the screen and then you do present now, and then you would hit either share screen or share window or something, and then you choose what you want to share.
Okay. So my question is just because the top two, let me see. Okay. Can you see?
Yes.
Okay, so these two,
Yep.
they're technically the same number.
They're
So
the same number. They just rounded the second one. Like whatever comes after 9 must be bigger than 5, and so they rounded the bottom one to the 1. But they're both square root of 2, like you said. It's plus or minus square root of 2.
so how do I know which one is the dominant eigenvalue if they're both the same?
They're both the same. They're both dominant. They have the same magnitude, and their eigenvectors will also be essentially the same. They'll be
So it doesn't
scalars.
matter which one you use?
It shouldn't matter now.
Okay, because I thought I tried using both and got different answers, but maybe I'm not doing it right.
So can you slide down?
Is that all correct?
That seems okay.
So
So it's an insect population. So if you go down again to those numbers, that makes sense because insects, they have lots of births and they don't live very long. So that's saying like 92% or almost 93% of the population are going to be these newborns because they're just insects don't live very long. And then very few, like less than 1% or about 1%, are going to be full-grown adults, 0.009.
okay.
Is that okay, Danny?
Yeah, I'm just trying to figure out my maple code real quick.
I thought you had some other question, though, brother. I thought you had a.
I did on, okay, so it was just for number 2.
Right, 2C, right?
For C, I didn't get the same answers as Maple got. I was just checking my answers in Maple, and
So did you do it by hand? Is that what you mean?
yeah.
Okay, can you show me Maple?
Yeah.
Real quick, was the one that Bradley just had up, was that was 5C in maple?
Yes.
Yeah, mine's way different.
What does yours say?
I got for dominant eigenvalue. Yeah, it was just I. And
Can
then
you slide back over to that one? Go to number 5 again, Bradley. Just make sure the matrix is right. Can you go to the top?
I wonder if it's because when you had it for like the Leslie matrix one, you had things defined as like F1, S1, S2. So I just rearranged those and then put them in again, but it's still the same. A is still the same, 20.1.2. But yeah,
If you get the same matrix, this should be fine. Do you want to share yours and show what you got?
Yeah, I need to like rejoin this call on my laptop because I don't have Maple on my big PC.
Okay.
But I can do that right now.
Yeah, let me look at Bradley's number 2. So, okay, that seems fine. So you get 8 minus 1 and 1.
So, yeah. Let me see where my work is. But did I get? Oh no, it's just 8, -1, -1.
Yeah, sorry, I misread that first. So -1 has multiplicity 2 is what that means. And so it comes with 2 eigenvectors. It comes with the 0, 2, 1 and the 1, 2, 0, 1, -2, 0.
So my, like, when I was row reducing and everything, I just basically the only difference is like I can't really like explain, but in my top row I had 1, 1/2, and 1, and then the rest were zeros. So I could make it look like their row reduced matrix if I flipped row 1 and row 2 and multiplied by 2.
So your first row in the one you did was 1, 1/2, 0?
1, 1/2, 1. That was my first row. And theirs, based off of like what they got as an answer, their second row was 2, 1, 2.
Think about that here. 1, 1/2, 0.
1, 1/2, 1.
Yeah, so this is the same. So can you see my screen? What I'm writing here? Yeah.
Yeah, that's what I got for answers, but that's not what Maple gives.
Okay, I agree. I think these are the answers.
That's what I got too.
Okay, so they just had all of the numbers in the second row, and they just had them multiplied by 2, I think, to get rid of the fraction.
Yeah, because I checked it somewhere too, and I think they did the same thing. It was a weird multiple of that, because I think if you just multiply it by 2, you get what Maple had, right?
If you multiply it by 2, but you also have to switch row 1 with row 2.
Oh.
That way, like V2 is
Can you go back to your Maple thing again?
Instead of solving for x1, they solved for x2.
Yeah, so I guess that's still true. Is that true?
But it's like different. You can't like, it's a completely different value.
Yeah, but you can switch the order of rows. So
Okay.
I do agree that seems strange. The first one worked out okay. Is that right? The 1, 1/2, 1. Is that correct? Yeah, that's just a straight scale of the other one.
Like, yeah, that was fine. So you can switch rows like in the eigenvectors as well?
I guess technically, but it seems strange to do. Like, I don't know why they would have done that. Yeah, I'll have to think about why Maple's doing that. But if you turn in what you got, like what I wrote here, then that's great.
So just to clarify, for 5B, I'm just using like, it's that simple. Like it's not a long thing. I don't have to.
No, it's a proof type thing. This is literally it.
Okay.
I'm still recording here. I just realized, so this will just be part of the thing I post online.
All right.
Is that it for you, Bradley?
I think I'm good then.
Okay, cool. I'm around if you need more help.
Okay. Thank you.
Bye. Danny, what else can I help with you?
How do I screen share?
You hover over and do present now.
Oh, there it is. Let's do my entire screen. I have to allow this.
You had done it before. You started doing it a second ago, I thought.
How do I? It's like a weird privacy setting. Chrome wants to. Oh, share. Oh my god.
Do you want to just email me your Maple code?
Yeah, I can do that. What? Let's see. All right, I just sent it. Oh wait. Now I just sent it. Yeah, so when I put it in, it, I don't know. I mean, you'll see it didn't. I don't know if it just didn't run everything right or what.
Hey, got it. Downloading. Opening. Okay, running. Let's see here. Okay, so that looks good. Notice how the problem here is it says, so dom ig val sort pulling out number 3 is what that says. So equation 3.
Yeah.
And that's correct. But then when you go to find the dominant eigenvector, you're pulling out the first entry. So change that number 1 to a 3 in the next line. So it should be the dom eigvec equals null space, blah, 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 blah. The very last number should be 3.
Okay.
Oh, no, that's not true, actually.
Okay. Yeah, that gave me an error.
Yeah, what just happened here? So I just ran everything again and just like changed. What the hell just happened? Now I'm getting zeros for everything. What is going on?
I don't know if it's like if I didn't change the defining A terms properly. I thought I did.
Okay, this works. Maybe I'll share my screen so you
Okay.
can see what I'm looking at here. Should have just done that before. Sorry. Okay, so you can see.
Yeah.
So make sure that it looks like this. So eigenvalues. So when you just do eigenvals and you don't put a 1 here, it like lists all the things. Like let me get rid of it for you. It shows like the eigenvalues over here and then their eigenvectors over here.
Okay.
And so when you put the 1 on it, it just pulls out the eigenvectors or the eigenvalues, I mean. And then you can see they're arranged in decreasing order with the biggest one at the top. And so I'm going to pick up the dominant one by choosing the thing we just sorted and picking out the biggest one.
So for some reason, mine won't even output anything for the eigenvectors A.
Oh, that's because you had a colon on this. You had it like that. So just delete the colon and then it'll print it out.
Oh, okay.
And so then the second thing should also have a 1 on it. So you pick out the biggest one.
For Dom eigenval.
Yeah, what I've got is just look at my screen.
Okay. Yeah, I just have to switch back.
And I think you might have had a 3 on this third one. I can't remember.
Okay, so I'll do a 1 and a 1. Okay, and then I have a 1 there.
I don't even know if you need a 1. Do you know? Let me see what happens when you get rid of that one. It just puts it in. It puts it in a bracket. So you just do a 1, so it pulls it out of the curly braces.
Okay, so now I think I have that.
And then you just normalize it. The last thing should stay the same. So you need these numbers to add up to 1, basically. And so the way you do that is you take each one and divide it by the sum is what that last thing is doing.
Okay.
And now those numbers add up to 1, and I still have Bradley's open. Oh, she didn't send me it. I don't have Bradley's anymore, but I'm pretty sure those are the numbers that she had in there. The last one definitely is, and I'm pretty sure the first one is, and that means the third one.
Okay, so I'll just print that out and put it as the answer for C?
Yeah, or you could write it down. You don't have to, whatever you want to do. You could just say like, I use maple and got this as the dominant eigenvalue, and this is the dominant eigenvalue.
Okay, and it's just that 1.4 plus point I.
It's square root of 2 is what it is. But yes. It's saying, so square root of 2 is 1.41, blah, 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 blah. And then it's saying it does not have an imaginary component.
Oh. Okay, so it's just the number.
It's just the number, which is, again, it's just square root of 2.
Okay. All right, so then. And then how do we know if it's growing because it's greater than 1?
Correct. The magnitude is greater than 1. So when you do the absolute value, it's bigger than 1. Yes.
Okay, that makes sense. So for number, all right, so that makes sense then. For 2B, so I was able to do like A and C by hand relatively easily. For B though, what's like supposed to happen with it?
For B, which one?
For 2B, like when you're finding the eigenvalues and eigenvectors for just A, B, B, A.
Mm-hmm.
Is it has to do something with it being?
Your answers are going to be in terms of A, B, C, or whatever.
Okay, because I ended up getting like a squared minus 2a lambda plus lambda squared minus b squared. So equals 0. So how do I like solve for lambda?
Quadratic formula.
Okay. And then, but so what would I just do? Like a squared minus b squared, is that would be the c term, like the constant technically?
It sounds like it. I don't remember. I could look at the answers real quick. But if you have an a squared minus c squared, that would be the constant term.
Yeah, because the vector itself is just a b b a, so there's only going to be a's and b's, right?
Oh, right. Yeah, right. And so yes, a squared minus b squared is the c term, correct?
Okay. All right. So I'll keep doing that out, knowing that.
I don't think you really need to do that. So you didn't need to multiply that out. Like you had a minus lambda squared minus b squared equals 0 first, right?
Yeah.
Just add b squared to the other side and then take a square root of both sides, and then you can just solve it that way.
Oh, okay.
You could either ones. You could just quadratic formula if you want. It's just maybe a little more straightforward doing that, a little more direct.
Oh, so you just get a minus lambda equals b, so
Equals plus or minus b.
Oh, right.
When you take a square root.
So it's just lambda equals plus or minus a minus b.
Lambda equals a plus or minus b.
A plus or minus b. Okay, and then it would, okay. So then you just do plug in a plus b, plug in a minus b, and go through it to find the eigenvectors. Okay.
Correct.
All right. I think that makes sense. Did we have Maple code to do stuff like for 7? Or it was like the LU factorization, or is that just kind of like just doing it out?
We don't have Maple code for it, but you can you need to multiply matrices and things like that to do that, and so you can use Maple to do the multiplication. That's what I would suggest.
Okay, so just like define the matrices in Maple and then just multiply them like that.
Yeah, you don't have to. You can do it by hand. You don't necessarily need to. That's how I did it when I did the solutions.
Okay. All right. I'm gonna keep working on this stuff then. I'll try to have it in by 5.
Okay. Let me know if you need some more time.
Okay, thank you.
Thank you. Bye.